Atmospheric convection comes in two different types. You have dry convection, which is when there's no contribution from moisture, and this occurs over dry land surfaces, so particularly if you think about a desert or a very arid surface, then you're going to have dry convection. But the more common situation is moist convection, and in this case, the evaporation from the moist surface and then the condensation of that moisture at some height in the atmosphere are important. And so this is the normal situation over the ocean or any wet land surface. And because you have the moisture, which can evaporate and then condense in the atmosphere, when it condenses, it releases heat, and this drives further convection. So as a result, moist convection tends to be much more vigorous. So we're going to consider these two things in order. We'll start with the dry case because it's simpler, and then go on and consider moist convection. In the atmosphere, convection is occurring predominantly in the troposphere. So that's below about 10 kilometers. And you can see the atmospheric structure shown on the picture of the right here. And so the troposphere is this region in the lower atmosphere. Once you get into the stratosphere, the fact that you have ozone in that region that's absorbing the sun's radiation leads to it being stably stratified. And typically it's too stably stratified to allow any convection. We saw an example of where a plume that's from the troposphere can project up into the stratosphere with the stratified plume volcano example from a couple of videos ago. But in general, the stratosphere does not have convection, whereas the troposphere convects all the time. And so the fact that you have this convection and this overturning occurring in the troposphere, it tends to keep the troposphere neutrally stratified, or even weakly stably stratified. Now, if you look at this plot of the temperature with height, and you'll see that, of course, the temperature is this red curve. So the temperature in the troposphere decreases with height. And I mean, you know this, you climb a mountain, it gets colder. And the rate of that decrease is something called the lapse rate, which is this factor or this parameter gamma. And that's about 6.5 Kelvin per kilometer. So if you go up to a 1 kilometer high mountain from sea level, on average, you'd expect the temperature to be about 6.5 Kelvin less. But you might find this a little confusing because I've just told you that the convection keeps the troposphere around neutrally stratified. And yet I've also just said that the temperature decreases with height. So we have warmer stuff at the bottom and colder stuff above. And you might say, well, surely that's unstable if you have that situation. And the reason it's not unstable is because of the influence of pressure on temperature. And so here in this plot, you can see the pressure that's shown in blue. So of course, pressure is much higher near the Earth's surface because you've got the whole weight of atmosphere sitting above you. So that's hydrostatic balance, means you must have higher pressure at the surface. And that reduces as you go up because you have less and less of the atmosphere above. And this pressure influences the temperature. And so we have to account for that influence when we're thinking about the stability or the buoyancy of the atmosphere. So how do we go about calculating buoyancy in the atmosphere? Because of this variation of the pressure with height, we need to use this thing called the potential temperature. So the variation of a gas's temperature with respect to pressure, you would see if you've ever used a gas bottle and you let some gas out, you'll notice the bottle gets cold. And that's because its pressure is reducing and therefore its temperature also reduces as a result, even though the heat content hasn't changed. So in climate science, we account for this using this thing called the potential temperature, which is defined here. So this theta is the potential temperature, T is the actual temperature, P naught is some reference pressure, and P is the actual pressure, and this R on Cp is a constant that's about 2/7 for an ideal gas. And what this does is it references the temperature to a uniform pressure. So we can say whatever pressure your air parcel is at, let's drag it down to a particular reference pressure, which we usually use the surface pressure, and compare the different potential temperatures at that fixed reference pressure. Now, if we do that, we actually get a direct comparison of the buoyancy of the particles, of the parcels of air. So the way you can compare buoyancy in an atmospheric context is using this potential temperature. You have to make sure everything you're comparing is at the same reference pressure. If you want to know how you get this potential temperature result, that was done in the second year Fundamentals of Climate course, and I've put the lecture videos below if you're interested in looking at that again, or if you haven't seen it before, if you're in the physics stream. So that goes through the different aspects of thermodynamics that leads to this potential temperature result, and it also describes how you can predict the lapse rate in the troposphere. So I'm not going to go through that again. The key thing here is if you're interested in buoyancy in the atmosphere, you need to compare potential temperatures, not actual temperatures. So once you've done that, and you know what your potential temperature is, you can go through and say, calculate the potential temperature at every height in this profile. And if that potential temperature increases with height, then you have a stable atmosphere. If it's constant with height, you have a neutral atmosphere. And if it decreases with height, you have an unstable atmosphere. And that's the situation where it's going to convect as a result. So usually we have a situation that's neutral or approximate or weakly stable, because if it is ever unstable, the convection acts to rapidly stabilize the atmosphere.